Hello everyone, I'm here to present our paper, Diffusion meets DAgger, Supercharging Eye-in-Hand Imitation Learning. Imitation learning is an effective way to train robots. However, it suffers from the well-known component execution errors problem. Small errors made by the learn policy lead a robot to out-of-distribution states, causing the learner to make even bigger errors. The current solution is to get expert actions on learner states, a strategy known as dataset aggregation or DAgger. However, it is hard to do in practice, and people often resort to collecting more expert data. In this paper, we propose a data creation framework, Diffusion meets DAgger, or DMD. For out-of-distribution states, DMD automatically generates observations and action labels. Our insight is, by replacing data collection with data creation, we improve sample efficiency of imitation learning. In more detail, we are given task data, which is a collection of trajectories collected by the expert. Each trajectory is a series of image action pairs. In this paper, images are views from an eye-in-hand camera, and the actions are relative end effector poses. Policy trained with only task data shows poor generalization. To address this issue, we use a function f to generate augmented dataset t tilde with out-of-distribution views and action labels. Delta p represents small perturbation from the original observation it. Here are three examples of perturbed views generated by f from it. Our insight is, access to this augmented dataset improves performance of the task policy. Closest to our work, Zhou et al. Spartan model trains NERVs on task data to synthesize out-of-distribution views. However, NERV assumes a static scene. Thus, it cannot reliably synthesize images when the scene undergoes deformation. For example, when the apple is moved to the target. Therefore, in this paper, F is realized using a conditional diffusion model that is pre-trained on large internet-scale data. We adopt a recent work from Yu et al. It conditions on a reference image IA taken by camera A and a transformation matrix that represents camera B's pose in A's frame. It produces view IB taken by camera B. We use a U-net diffusion model, which given a noisy image IBT at step T and the diffusion time step T, is trained to produce the noise epsilon added to the image. Rather than directly denoising in the high-resolution pixel space, the denoising is done in the latent space of a Vikugan autoencoder. We explain more in details of how the original paper conditions on the camera pose information. Given camera intrinsics and extrinsics matrices, and an image taken by the camera that has dimension h by w, we want to represent the camera model using the camera ray direction at each pixel UV, which is given by. We also concatenate the ray direction with the camera center. So instead of using a 3x4 projection matrix to represent the camera, this representation would be h by w by 6. Please see more details in section 3.2 of the original Yu et al. Paper. For training the model, we collected data on a grabber tool. Task data includes 24 expert demonstration trajectories. We also collected play data, for which we move the grabber around the apple and push it in many different directions. This only gives us image sequences. To extract camera poses, we use COMAP, a structure for motion library. For each trajectory, we sample random pairs of images to produce triples IA, IB, and the relative transform that are used to fine-tune the diffusion model. To learn a policy for the downstream task, we augment our task data using the fine-tuned diffusion model. First, we need to generate out-of-distribution views. We condition on a given image IT from an expert trajectory. We also condition on a small perturbation delta P, which corresponds to translating the agent along a randomly chosen direction. An out-of-distribution image taken from the translated camera is then generated. In order to use this generated image to train the task policy, we also need to annotate with an action label. In the trajectory containing IT plus k is a future observation at time t plus k. AT is the action that moves from IT to IT plus K. The action label for IT tilde is simply the action that would convey the agent from the pose depicted in IT tilde to the pose in IT plus K. The task data and the augmented dataset are then used to train the task policy, which is implemented using a ResNet 18 backbone followed by linear layers. On the robot, the task is to push an object to a target location marked by a red circle. It requires both reaching and pushing the object. Observations come from an in-hand GoPro camera. The action space is relative 3D translations of the end effector. For the first baseline, we use vanilla behavior cloning on the expert data. We refer to this baseline as BC. We also compare to Spartan, which trains nerves on demonstration data to synthesize out-of-distribution views. We conduct offline experiments to compare with the baselines and other data augmentation schemes. The training set consists of the aforementioned 24 trajectories. The validation and test set contains 23 and 27 trajectories respectively. The metric is median angle between the predicted and the ground truth translation. Here we show one part of the offline results. We see that DMD outperforms both baselines on the test set. Details about other offline evaluations can be found in the paper. We next show some qualitative visualizations. Here are images from the original expert demonstrations. These are images generated from the diffusion model when the perturbation is movement to the left, to the right, forward, and backward. The model is able to faithfully synthesize different views with minimal artifacts. Compare images generated by the diffusion model to those generated using a nerve-based approach from Spartan. The moving object breaks the static scene assumption made by nerve. Thus, Spartan masks out the gripper before training the nerve and learns policy for the grasping task. This strategy fails in our task, since pushing will inevitably move the object. To use nerve for our task, we experiment with different masking schemes, masking just the gripper, masking the gripper and the moving apple, and no masking. No masking leads to the worst results as expected. Masking just the grabber causes the moving object to blur out. Masking a larger region around the grabber fixes the blurring but also eliminates the apple, making these augmented samples difficult to use for training the downstream policy. In contrast, images synthesized using our diffusion model move the camera as desired. Our online experiments measure the success rate at the non-prehensile pushing task. We conduct 10 trials per method and randomize the apple start location between trials. We find the vanilla BC model to get a 30% success rate, while DMD achieves 100%. Here are the execution videos for the BC baseline. Here are videos for DMD. Compared with Spartan, DMD succeeds 100% of the time, but Spartan only succeeds 50% of the time. Here are videos of Spartan. The significant difference shows that minor errors at each step can accumulate and result in task failure. Motivated by the 100% performance with 24 demonstrations, we want to know how low can the number of demonstrations be. We consider two low data settings with 8 and 16 demonstrations. For these settings, the diffusion model is trained with only play data and has no access to the 24 demonstrations. We see that DMD maintains an 80% success rate with only 8 demonstrations. Here are the videos of DMD with only 8 demonstrations. Here are videos for the BC baseline. Videos of the 16 demonstration experiment can be found at the end of the video after the summary slide. We also experimented with the choice of dataset for training the diffusion model. We repeat the 24 demonstration experiment, but vary the diffusion model that generated the augmented dataset. Using the diffusion model trained on just task data leads to an 80% success rate, versus 100% success with the diffusion model trained on both task and play data. We conducted an experiment on another object, a cup. The BC baseline achieves 80% success, while DMD achieves 90%. Videos of these experiments can be found at the end of the video after the summary slide. In summary, we propose a data creation pipeline, Diffusion meets DAgger, that automatically generates observations and action labels for out-of-distribution states to tackle the compounding execution errors problem in imitation learning. We adopt diffusion model over NERV so that our method can handle tasks involving scene deformation when robot interacts with objects in the environment. Moreover, we demonstrate robust performance of DMD on non-prehensile pushing tasks. DMD can achieve a success rate of 80% with as few as 8 expert demonstrations, where naive BC reaches only 20%. DMD also outperforms competing nerve-based augmentation schemes by 50%. Thank you. Here are the execution videos of the BC baseline for the 16 demonstration experiment. Here are the execution videos of DMD. Here are videos of a policy trained with augmented images generated by a diffusion model with only task data. Here are videos of a policy trained with augmented images generated by a diffusion model with both task and play data. Here are videos of the BC baseline for a new object, cup. Here are videos of DMD for the cup.